Good evening, everyone. Welcome to another session of the Network Seminar Series hosted by the Center for Networked Intelligence at the Robert Bosch Center for Cyber Physical Systems, IISc. Today's talk is by Dr. Arpan Mukhopadhyay, and he will be speaking on the power of little job parallelism for latency reduction. Dr. Arpan Mukhopadhyay received his BE degree in Electronics and Telecommunication Engineering from Jadavpur University, India in 2009, ME degree in Telecommunications from the Indian Institute of Science, India in 2011, and the PhD degree in Electrical and Computer Engineering from the University of Waterloo, Canada in 2016. He is currently an assistant professor at the Department of Computer Science, University of Warwick, UK. His research interests include applied probability, stochastic processes, algorithm design, and optimization with applications to computer and communication networks. He has received Best Paper Awards at IFIP Performance 2015 and the International Tele-Traffic Congress 2015. He was also awarded the Rising Scholar Award at the International Tele-Traffic Congress 2018 for his contributions to mean field analysis of large heterogeneous networks. Before we move on to the talk, we would like to request the audience to subscribe to our Google group for information on future talks. You can also visit our website for more details. I will be pasting the links in the chat box. Please do check. Finally, we request the audience to keep your microphones on silent for the duration of the talk. And for questions, you may ask Professor Arpan directly or type them in the chat box and we'll moderate it with him. Over to you, Professor.
Thank you very much for the kind introduction. And also thank you to the organizers for inviting me to this seminar series. It is really an honor to speak to this audience, and it's nice to see some familiar names in the audience list as well. Okay, so the talk today is titled On the Power of Little Job Parallelism for Latency Reduction. And this work is basically about the effects that parallel processing of jobs has on the reduction of latency in large-scale systems. And this is a joint work with my collaborator, Ayalvari Ganesh from the University of Bristol. Before I move on, let me just mention that if you have any questions at any point, please feel free to interrupt me. I will try to give pauses during my talk to take questions, but if you have any questions in between, please feel free to interrupt me at any point, okay? Okay, so without further ado, let me get started. So I'll start with some motivation. So we are currently living in an era where most modern computation-intensive jobs can be made highly parallelizable, which means that they can be programmed in a way such that they can run in parallel on large number of processing cores or units to speed up execution. For example, machine learning jobs or machine learning models can be trained using this open source software package called TensorFlow. And TensorFlow provides a lot of tools or APIs to make computations or distribute computations across multiple devices or multiple servers. So the real benefit of processing jobs in parallel at multiple cores is to reduce its processing time or latency. However, if you want to process a job in parallel by multiple threads, we need to also synchronize these parallel threads to avoid synchronization errors. For example, a common synchronization errors include race conditions or deadlocks and things like that. So in order to avoid such synchronization errors, we need to properly synchronize the parallel processing threads. And this introduces communication overhead between these parallel processing threads, or if you are processing the servers at multiple if you're processing the job at multiple devices, then it introduces communication overhead between the multiple devices. Okay, so so the real question that we are interested in this work is that can we achieve significant reduction in the latency by using only a small number of cores per job? Clearly, in order to speed up execution, we need to have more parallelism. But as I just mentioned, more parallelism also means that more synchronization needs to be maintained between parallel threads, and therefore it adds to the communication overhead. So we want to make the communication overhead as small as possible. So the question is whether we can gain significantly in terms of reduction in the processing time by using only a small number of parallel processing units per job. So this is the main question that motivates our work. And based on this motivation, we considered the following model in this work. So our model consists of n identical processor sharing servers. And these servers are shown as these blue circles in this figure. And a job needs d servers to process. So here, d is called the degree of parallelism of every job, or because this is we are considering a homogeneous system, we have the same degree of parallelism for all the jobs. Okay, so one can think of this system as a network or a graph where the nodes are the servers as shown in these blue circles, and the edges are basically the jobs. Okay, so so for example, here we are considering the case where d is 2. So every job requires 2 servers exactly to process. So an edge between 2 nodes will mean that this is a job. So this yellow edge is a job which is using both server 1 and server n here. Similarly, this 2 green jobs are using this server here, server n, and server 2. Okay, so in this system, because d is 2, every job will use exactly 2 servers. But one can also extend this model to d greater than or equals to 2, where you have to consider a hypergraph where every edge connects d nodes, not just 2 nodes. Okay, but for simplicity, we will just use d equals to 2 to visualize the model. We assume that the servers are processor sharing, and each server has a total capacity of 1 unit, and this is without a loss of any generality. And because the servers are processor sharing, every job residing on a particular server will get equal fraction of the capacity of that server. So for example, on server n, we see that there are 3 jobs because there are 3 edges attached to this server. And because of that, every job will get exactly 1/3 of its capacity. Okay. Similarly, at server 2, each of these 2 jobs will get 1/2 of the capacity, and the yellow job here will get the whole capacity from server 1. Okay, so this is the scheduling policy that we will consider, and we will, for simplicity, the occupancy at a given server will be called the queue length of the server. But note that there is no queue, no actual queue in the system, because all the jobs residing on a server are being processed in parallel. But just for simplicity, we will use the term queue length to say the server occupancy. Okay, so the server occupancy will have the same meaning as queue length. Okay. So
Can I ask a question, Arpan?
we also, yes, sure.
Sorry. So I'm having trouble with understanding this. Why does each job need D servers? Because in some sense, it's not like like you're giving. So you're giving service proportional to how many jobs are there, right? Which is not in your control. I mean, you have certain job size, but is there a particular reason you want them to use D servers?
So that's a valid point. I think what you're trying to say is that your question is sort of why is all the jobs require exactly D servers? Is that correct?
No, maybe why D servers, right? So there are two ways I can think of people do it, right? One is that you have subdivided a job, and you want this subdivision to get done, like so divided in D parts, right? Or you give the same job, and if any one of the D does, then you cancel D minus one. But here I don't know what the notion of D is that are they doing D different jobs and that every job needs to be done by D of them? Yeah, sorry, go ahead.
Yeah, I'm going to explain that. So what this means, so I will, in the next slide, I will explain how exactly these, a given job, suppose it is shared by, it is using two servers, how is it exactly processed? I will describe that. It is not exactly the redundancy model that you are talking about, where we are sort of dividing the job into two parts and then sending the two parts into two different servers. It's not like that. I will very soon talk about how exactly we are processing it. Okay, so I'll talk about it right in the next slide. So if you still have questions, please do raise it again. Okay. All right. So so we will assume that the arrival rate of jobs to the system is n lambda. Okay, sorry, this should be small n, not capital N. This should be small n, where small n is the same as the number of servers in the system. And we have to have lambda less than 1. And this is just to make sure that this is a necessary condition for stability, because we have assumed that the total capacity of the entire system is n, because we have n unit rate servers. So we cannot possibly support an arrival rate more than n. So obviously lambda has to be something less than 1. And we will also assume that the job sizes are IRD exponential random variables, each having mean 1. Okay, so this is the model assumption. Now I'll just describe how do the servers select the D servers. So once a job comes in to the system, so for example, here we are showing the red job, which has just arrived. Then it will pick the D servers uniformly at random from the N servers. Okay, so for example, in this case, this red job just selected servers 1 and 2. Now coming back to the question that how are the jobs processed? So I'm not really dividing the job a priori and sending those parts to different servers. What we are rather doing here in this model is that we are allowing the servers to process the jobs from using two different threads. For example, you can think of this red job here being processed by servers 1 and 2 from two different ends. Okay, so for example, server 1 will start a thread from this end, and server 2 will start another thread from this end. And when these two threads meet, that means that we have completed the entire job, and then the job will leave the system. Okay, so in other words, what it means is that at every instant of time, a given job will get the rate. So suppose this a job sees the queue lengths qj1 to qjd at these d different servers, which is processing the jobs. Then at any given instant, it will see a rate of 1 over qj1 plus 1 over qj2 up to 1 over qjd. And the job leaves the system as soon as the amount of work done by all D servers equals its size. So we don't divide the job a priori, but we let all the D servers work on it together. And when the total amount of work done by all these servers are equal to the original length of the job or the size of the job, then we say that the job is complete, and then it will leave the system. Okay, so this is the processing model that we have considered in this work. Okay, I hope so. I'll take questions slightly later.
Thanks, Arpan. This clears, but now I'm clear what it means. So basically, you're saying that look, the D is not important. So D is sort of your parallelism parameter, right? If your D is large, you'll have more communication. Absolutely. I mean, ideally, you can have D to be N, right? Because that will give you the best performance. That's what my guess would be, right?
Absolutely.
But because your overhead, you want to minimize it, and that's why you're selecting a D much smaller than N. So that you don't have overhead. Okay, it's clear. Thank you. So it's not that you want the same amount of job to be done by all. The sum has to be equal to the size which you have. Okay, thank you.
Yes. So exactly as Parimal mentioned. So this is so we are not dividing or prioritizing the job, but we are letting all the servers, all the D servers work on the job together. So D, you can think of as the degree of parallelism in the system. So obviously, as D increases, we will expect that the processing time of a job will decrease, but it will come at a cost of very large synchronization overhead between the threads that are working on a job. And that's why we want to sort of keep D small compared to N. Okay, so there is a trade-off between high D and low D. So that's not hard to see. Okay, so the performance measure, as I just described, are essentially two things. So we are interested in two quantities. One is the average job delay, which is the average time that a job spends in the system at stationarity, and the communication overhead, which obviously increases with the degree of parallelism D, right? And the goal is to reduce the average delay, keeping the communication overhead as low as possible. And one way of doing that is to keep the product D times the average job delay as low as possible, because we want to sort of have this whole product as small as possible, because we don't want too much communication overhead, but we also don't want too much delay of a job. So we want to sort of keep this product as low as possible. And we call this product as the delay overhead product. Okay, so we will see soon that in fact this delay overhead product is directly proportional to the average queue length of the system. But let's call it the delay overhead product. Okay. All right. So is there any question? Yes, of course.
Yeah. So in this, how do you quantify the job delay? Is it time spent in doing actual work, or time spent waiting for synchronization between multiple the D threads?
It is the time. So the delay is defined as the time that the job spends in the system, from the time it enters the system till the time it leaves the system. As I mentioned, the threads or the processors are working in parallel to process the job, and the moment the total sum of the amounts of work done by different threads is equal to the total size of the job, the total size that the job has brought in, the job is considered as complete, and then the job will leave the system. So I'm talking about the time till from the time the job enters till the time it leaves. So this is the job delay.
So in this case, how do we model this synchronization between threads? Or are the processors able to complete the task of a job without waiting for each other? Like, can they independently go to completion?
Yes, so that's a good question. So we are not really bothered too much about how exactly we are doing the synchronization. In that sense, this is sort of an idealized way of processing the job. We are really interested in looking at the effect that the degree of parallelism has on the system's performance. We are not going into too much detail of how the synchronization will be achieved by the parallel threads. But one way of thinking of this, if you think of the d equals to 2 case, is that suppose we use, say, synchronization primitives. If you're familiar with them, for example, if you're using mutex locks and things like that. So before proceeding to fetch every part of the job, so suppose we are doing a matrix multiplication, to fetch every row. Before fetching every row, we have to sort of first unlock a lock and then lock it again, so that no other thread can work on the same thread at the same time. So if two threads are doing the same thing using the same lock, then it is possible to do the synchronization between the two, right? So so obviously at every step you have to first acquire the lock, then do the processing, then release the lock. So that's one way of doing the synchronization. But this is obviously you can see that as the number of threads increases, it will also cause more and more communication overhead. So this is one way of synchronization.
So one more question. How is this job size related with D? Is there some correlation between them?
No.
Just a quick interruption. Arpan, could you keep the previous slide on while you respond to this question?
Oh, yeah, sure. No problem. Yes. You mean this slide or the one previous to this?
No, the next slide is fine.
Okay.
Sorry, go back one step.
Yeah, okay. Good.
Yeah, this is enough. Yeah, thanks.
Yeah, okay. So yeah, sorry, your question was whether a job size is correlated with D, and this is not our assumption. We are not assuming that job size is anyway correlated to D. We are simply assuming that the job sizes are IID exponential random variable with unit mean, okay? Okay, does that answer your question?
Yes, thanks.
Okay. So
one more question, on, maybe very simple. So I think this, now you skip this delay. So it is clear that when you increase D, your delay would go down, right? Just maybe next slide. No? So, so you came up with this. Is there a meaning for this delay bandwidth product? Other than what the formula will say. Like, is there an operational meaning? How did you come up with this objective?
So this is a very rough approximation of, I mean, it's not a very sort of concrete way of measuring the performance. We know we are not really interested in exactly how communication overhead increases with D. We know that it increases with D, and we know that we want to sort of minimize the average delay. So we just take the product of the two. It's sort of the first approximation of this thing. I mean, it's not a very carefully chosen.
The reason I'm saying that, I could have taken maybe just a linear combination of these two, right? D plus lambda, right? But you took this, which probably led to something interesting. So I was just curious.
Yes, so that's true. I mean, this, correct. So this actually, we will see very soon that this this product is basically the average Q length of the system. So that's one way of saying that, sort of motivating this.
But that you got after you did the analysis, right? For fixed D, this you would not have known about.
Yes. Right. But yeah, it's kind of we started off with this, but then we saw that it's very. It's a very convenient metric to work with. It later turned out to. Yeah. Okay.
I have a question. So in your model, D is fixed for all jobs, right? So suppose
D is fixed for yes.
Okay. And another clarification, that is there any scheduler who is scheduling the jobs, or it is completely distributed?
It is completely distributed. So we are assuming that once a job arrives, it is free to choose any D servers in the system.
Okay, thank you.
Shall I move ahead? Okay. All right, so let's consider the two extreme cases. So first is the d equals to 1 case. So in this case, obviously each job randomly picks one server in the system and joins that server. And in this case, it's not difficult to see that we essentially have n independent servers, each having an arrival rate of lambda because of this Poisson splitting property, because every job is choosing a given server with probability 1 over n, and the rate is n lambda, so every server gets a rate of lambda, and the service rate is 1. So this is just an MM1 queue, right? We know exactly what the queue length is for an MM1 queue. So the average queue length in this system is just lambda divided by 1 minus lambda. And just by Little's law, we know that the average job delay in this system is 1 over 1 minus lambda, right? So this is already known. Now, if you compute the delay overhead product for this system, it's d times the average job delay, which is 1 over 1 minus lambda, and d equals to 1. So this is just 1 divided by 1 minus lambda in this case. Okay. Now let's consider the opposite extreme where d is chosen to be n. So this is the fully resource pooled system. So we are using all the servers to process any job in the system. So in other words, once a job comes in, it joins all the servers. And this system is also easy to analyze because it works as a resource pooled system where the arrival rate is n lambda and the service rate is n, because every job is getting service from all the servers. So it's a resource pooled system. So you can think of all the servers being combined into one large server, which has rate n. And that server has a Poisson arrival rate of n lambda. And in this case, again, this behaves as the MM1 queue with n lambda arrival rate and n as the service rate. And we can easily compute the average queue length to be lambda divided by 1 minus lambda. Again, the same queue length as we saw for d equals to 1. But the average delay by Little's law will be 1 over n times 1 divided by 1 minus lambda. So this clearly is n times lower than the d equals to 1 case, because in the d equals to 1 case, we didn't have this n factor in the denominator. So this is obviously much better, but clearly it comes at the cost of increased communication overhead between the threads. So the delay overhead product is d times this, but d times the delay, and d is n. So this is just 1 divided by 1 minus lambda. And this is the same as in the d equals to 1 case. So in terms of the delay overhead product, d equals to n is no different from d equals to 1. Okay, so both are equally good or equally bad. Okay, so although we are getting a much reduced delay, but the delay overhead product is still sort of the same as d equals to 1. So the question is, what if we choose d in between 2 to n minus 1? And this we can easily simulate for small n. So here, for example, we have taken two systems with n equals to 10 servers and n equals to 20 servers. And we have plotted the delay overhead product as a function of the parameter or the degree of parallelism d, and for lambda 0.9 for both cases. And you can see that it sort of, when we increase d from 1 to 2, we have a sharp drop in the delay overhead product, and then it slowly increases. And finally, when d reaches n, it becomes the same as the d equals to 1 case. And similarly, for n equals to 20, we see the sharpest drop happening from d equals to 1 to 2. And then there is a small further delay for some time, and then it eventually increases and goes to the same value as d equals to 1. So this is how it looks for d in the range from 2 to n minus 1. Even if you look at the average delay of the jobs, we see that the average delay also has a sharp decrease when it is when d is increased from 1 to 2. And after that, if we keep on increasing D, then obviously the job delay reduces, but the reduction is not that significant as in the case from D equals to 1 to 2. Okay, so this is the same trend for both n equals to 10 and n equals to 20. So the sharpest drop we see is from D equals to 1 to D equals to 2. Okay, so this is our key observation from this numerical plots. So the question which naturally arises is, can we characterize the performance of the system analytically for small values of D? For example, if we choose some D greater than or equals to 2. And our aim is to really study the performance of the system as n goes to infinity for some fixed value of D greater than or equals to 2. And this motivation comes from the fact that most of the modern systems are very large, because they will have a large number of processing units of the order of hundreds of thousands. So really, if we can characterize the performance of the limiting system as n goes to infinity for some fixed D, then it will be an accurate approximation of the finite system as well. So this is the main goal of the work. So I'll just give you an overview of the main results that we have. It will be not a detailed overview, I mean, not the technical results in detail, but just an overview of the results. So using mean field approximations, what we see is that for fixed D greater than or equals to 2 and large n, the delay of the average delay of the jobs in the system is roughly of the order of 1 over lambda times log of 1 by 1 minus lambda, when lambda is close to 1. So lambda close to 1 means that we are reaching the capacity of the system. And when lambda is close to 1, we see that the average job delay is of the order of 1 over lambda log 1 by 1 minus lambda. And you have to compare this with the D equals to 1 case, for which we know that the average delay is just 1 by 1 minus lambda. So if we compare the two results, we see almost an exponential reduction in the average job delay just by choosing a small value of D. Obviously, this is in the limit, in the mean field limit, but for large enough n, we will see a significant reduction in the delay performance or the delay of the jobs if we just go from D equals to 1 to D equals to 2. Okay, so this is sort of the main takeaway message of our work. But we also make significant progress towards rigorously establishing the mean field approximation. So I'll try to discuss the technical results that we have so far for this model. Okay. So before we go to the analysis part, let me just introduce some preliminary notations. So the Q length of server J at time t in the system with n servers will be denoted by Qnj of t. And this Qn of t will be called the Q length vector, which consists of the Q lengths of all the servers in the system. And the Q length process is basically just this Q length vector process over time. And it's not difficult to see that this process is non-Markovian. Why? Because if you just look at one particular server and you try to compute the rate of departure of jobs from that particular server, it is not sufficient to just know the Q lengths of all the other servers. We also need to know the exact sharing of the server. So for example, we have to know which job is shared with which other server. Unless you give me that information, we cannot compute the departure rate from a given queue. And this is why this process Qn is not a Markov process. And this is unlike many other systems, many other similar models that are looked into the literature, where the Q length vector is Markovian. But in our case, it is a non-Markovian process. And this is one key difficulty in our analysis. Okay. All right, so let's denote by pi n0 of tk the probability that the Q length at the jth server takes the value k, given that the system starts empty. Okay, so we start at 0, empty system, and we are asking what is the probability that at server j we have k jobs at time t. And one important thing to note here is that this probability will not depend on the index of the server j. Why? Because the rule of the jobs selection rule of the servers doesn't distinguish between the servers, right? So for a given job, all the servers are the same. So it will pick any d servers from the n servers uniformly at random. So therefore, if the system starts in a state which is symmetric across all the servers, then it will remain symmetric throughout all the times. So this probability will not depend on j. So this is an important property that is used in the analysis. And in general, this property can be generalized to the case where Qn0, which is the initial state of the system or initial Q length vector, this is distributed according to some distribution nu, which is exchangeable. Exchangeability means that essentially we can permute the indices of the servers and the distribution will remain the same. Okay, and that again just comes from the property that we are every job is selecting the same so the d servers uniformly at random. I think there is a question by Rajesh.
This is Rajesh here. So I think the question is related to the comment that you made that the Q process is not Markovian.
Yeah, okay.
I think I understand the statement when you say that Qn0 is 0, there is symmetry. But
yes.
If you say Qn0 is exchangeable with some distribution nu, then there could be some load, the state of each job, how much it has been executed in this queue versus another queue. Somehow that additional information, isn't it needed? Is it obvious that the exchangeability continues for all time? I understand that if nu is delta 0, then it's okay. But if it is not,
yeah. So we are, we actually this you're right. So we have to. I mean, the initial we are assuming here not. Probably I should have used the actual state. So this is what I meant to say is the whole state. I mean, if you include all the additional information about which job is being shared by which server. So if everything is initially symmetric, okay, so then it should be the distribution at any time should not depend on the server index. You're right.
Okay, thank you.
Okay, so this is not completely correct, as Rajesh pointed out. So this should be actually the entire system state. What do I mean by entire system state? I will come later, but this is an important point to note down. Okay, so all right. So the system performance depends on the stationary distribution of the queue lengths at the servers, and this we will denote by pi n without any time. And this is obviously a distribution over the integers, non-negative integers. And this, if it exists, it should not depend on the initial distribution of the system, which is nu. Okay, so remember that we denoted this distribution starting from the initial distribution nu as pi n of nu, and this limiting distribution should not depend on this initial distribution if the system is ergodic. Okay. All right. So this is some preliminary notation, but we said that the measure pi n, which is the distribution of the stationary distribution of the queue lengths, should determine the performance of the system, and this is a justification of this. So if we know this distribution of the queue lengths, then we can compute the expected queue length of each individual server under pi n. And then the total queue length in the system will be just n times expected value of pi n of q. Because again, this comes from the symmetry property. So because our stationary measure does not depend on the initial state we have started with, so we can assume that we have started with all 0 state, and therefore we have remained exchangeable throughout all times. So at stationarity also we are exchangeable, and therefore our total queue length is just n times the expected queue length of one individual server. And the number of jobs in the system is therefore 1 over d times this. Why? Because every job, remember, is shared by d servers. So if we have the total queue length, we have to divide it by d to get the actual number of jobs in the system. So this is the total number of jobs. And the average delay, obviously by Little's law, we know that the average delay is 1 over the arrival rate times the number of jobs at stationarity. And this is just 1 over d lambda times the expected queue length at a given server. Okay. And therefore, the delay overhead product is just d times 1 over d lambda of expected queue length. And this is just 1 by lambda of expected queue length. And so we see that the delay overhead product is simply just the proportional to the mean queue length of the system, and the proportionality constant is just 1 over lambda. So for most performance analysis, we will only focus on the expected queue length at a given server. Okay.
I have a question on
this,
Shrikant. In one of your earlier slides, when you put this, whatever the delay product, that factor log 1 over 1 minus lambda, that goes to infinity, right? When is there a reciprocal or something missing in the previous? No, the one before.
Yeah.
This one, next one.
Okay, sorry. So this is 1 over log of, this is going to infinity as lambda goes to 1, that's true, but this is order of this, which means that obviously we as lambda, so this order is as lambda approaches 1. So so this means that the delay, average delay, will be bounded by some constant times this quantity for sufficiently large lambda close to 1. Okay. But
so
not exactly.
Are you saying that you get an exponential this thing? So your case d equal to 1 was 1 over, I see, 1 over 1 minus lambda. I see, got it. Yeah. So instead of 1 over 1 minus lambda, you have a log 1. Okay. Yeah. Right. Thanks. That's right.
All right. So the key question, because we just saw that our model is non-Markovian, so the queue length vector is non-Markovian. So in that case, can we prove that the stationary queue length distribution even exists? So that's the first question. And then if it exists for each n, what we really would like to study is the limit of this sequence of stationary measures as n goes to infinity. And if it exists, we will call it pi. And we will have to obviously talk about in what sense we should consider this limit. One way of talking about this limit is to take the total variation distance between pi n and the limit. So if there exists a distribution pi such that this sequence of pi n converges to pi in the total variation distance, then that is a good distribution that will characterize the limiting performance of the system. And if this limit exists, if such a pi satisfying this exists, then what we are really interested in is how does pi depend on d, right? So this is the degree of parallelism of the system. So what we want to study is how pi varies with d. Okay. All right. So the challenges, as I mentioned before, is that Qn is non-Markovian. So in order to analyze the stationary distribution, we have to find a Markovian state descriptor of the system and express the Q length vector as a function of this Markovian state descriptor. Okay, and but even if we do find a Markovian descriptor, even then analyzing pi n for finite n is quite difficult because of the complicated interaction between the servers. Note that the state of a given server will depend on the state of all the other servers with which it shares a job. And this dependence is not just instantaneous, it will persist as long as the job will remain in the system. And this is one important difference between our model and other existing models in the literature, where the dependence between servers is instantaneous at epochs. But here we have the dependence which is persisting as long as the job is in the system. Okay, so because of this reason, analytically solving the global balance equations for this system to determine pi n for finite n is almost impossible. So we try to characterize the limit of pi n if it exists. Okay, so so this is the traditional way of doing this. So we generally look at the empirical measure process, which we call by as a small pn of t. So this is basically a distribution of the Q lengths at any time t in the system. So pn of tk is basically the measuring the fraction of servers that fraction of servers with Q length k at time t. So this is a measure valued process, and if it satisfies, okay, so this measured value, this is a measure value process, and if the system is ergodic, then it can be shown that this measure valued process will in the limit as t goes to infinity will converge to the stationary distribution or stationary Q length distribution of one individual Q pi n. Okay, so if ergodicity is true, then this limit is true. But what happens as n goes to infinity? So if this empirical measure process satisfies some nice conditions, then we can use some well-known results to show that this process goes to a deterministic process pt in the limit as n goes to infinity. And those conditions that are needed to prove this are basically captured by this term density dependent Markov processes. So if the rates satisfy certain structure, then we call it density dependent. And in that case, using Kurt's theorem, Kurt's type theorems, we can show that the limit of this process is in fact deterministic and given by and it is given by an ODE system of ordinary differential equations. And furthermore, if this PT is a globally stable process, or in other words, if it has, as t goes to infinity, if it converges to a global attractor pi, which is called the global asymptotic stability property, then we can show, under mild conditions, we can show that in fact, this limit of pi n, the sequence of stationary distribution indexed by the system size, will converge to this global attractor pi as n goes to infinity. So this is the regular way of finding the limit of this pi n sequence of distributions. But in our case, unfortunately, the process Pn is not even Markovian. So we want Pn to be a density dependent process to density dependent Markov process to apply Kurt's theorem. But in our case, it's not even Markovian, so we cannot apply the well-known results. And the question then is, can we still get a deterministic limit of this process Pn, which satisfies the global asymptotic stability property with some attractor pi? And the answer to this question in general is not known. For some specific cases, there are models, but in general, we do not have answers to this question. Okay. All right. So I should probably just pause for a few seconds to see if there are any questions at this point.
I have a question, Rajesh.
Yes.
So one way by which you could try to utilize previous results, if you could go back to the previous slide where you said it is not a Markov process, perhaps there is an embedding of this process by enlarging the state space to turn it into a Markov process. And maybe then the old results may still be applicable, might still be a complicated one, but you might still be able to get something and then project it onto the P space and maybe get the results. Is such an approach not amenable in this particular situation?
Yeah, so I will describe. I haven't described the Markovian descriptor of the system yet. So we have a Markovian descriptor. We will discuss that. We can sort of describe Pn as a function of that Markovian state descriptor, but even that Markovian descriptor that we come up with, we have tried different state descriptors. In this case, it seems that we haven't been able to find so far a state descriptor which satisfies the conditions of Kurt's theorem. So we cannot sort of directly apply those type of theorems to our system where we have a very different kind of Markovian state transitions.
The Kurtz's theorem that you're thinking of, should you be looking at the Markov process? I mean, is it the Markov process generator? The Markov process generator converging to some first order operator, or is it a specific Kurt's theorem that you're looking at?
Yeah, so Kurt's theorem, I'm basically I'm talking about this very basic theorem where you do the first order approximation of the generator and then look at the limit, and it converges to this differential generator of the differential equation, and then you from there you basically argue that the process will be convergent. So this type of theorems, and they have been extended to various cases. For example, what happens to infinite dimensions and so on. But originally by Kurtz it was just for finite dimensions, but now we know much more about this type of results.
Okay, so
but none of
your result is one of those extensions that which has, I guess that's the novelty.
Yeah, exactly. Okay, so I will I do not have too much time, I guess, to describe the related work. So let me just talk about a few related works, because Rajesh asked this question. So there are some models which look at systems where the finite n empirical measure process is non-Markovian, but the limit, if you look at the limiting process, the empirical measure process becomes a nonlinear nonlinear Markov process. And there are certain works like this. For example, these two works are of this category, but really their systems are much simpler than the system that we are considering, and there is no general result that we can apply and say, well, this would be the case even in our case. So we have to do the analysis for our specific system model using our specific rates and so on. So we have to do all of that. Okay, and the approach that we use throughout the work is the approach devised by Bramson, Liu, and Prabhakar in this 2012 paper, which proved asymptotic independence using some branching process arguments. Although we are not able to exactly extrapolate this branching process argument to our case, because as I mentioned before, the branching process argument doesn't work because our dependence between the servers is not instantaneous. It persists for some interval of time. Because of that, it doesn't work in that way. So let me jump in and discuss the first result. So the first result states that for lambda less than 1, the stationary Q-length distribution exists and is unique, and we have a uniform bound on the stationary Q-lengths over all n. Okay, so this is the first rigorous result. Okay, which basically shows that the system is ergodic for lambda less than 1, which is the natural stability condition, and it also gets a uniform bound on the Q-length over all n. Okay, and what this means is that the sequence of stationary distribution is tight. Okay, so the probability that the Q length lies outside a compact set is basically bounded arbitrarily by a small number as you want. So you can make epsilon as small as you want. So this just follows from Markov inequality from this bound that we have obtained, this uniform bound that we have obtained. Okay, so how is this result helpful? Because the tightness of this sequence of measures implies by Prohorov's theorem that there is a convergent subsequence of this sequence of probability measures pi n. Okay, and what we are really interested in is the limit of this convergent subsequences, because we want to study the system's performance in the limit as n goes to infinity. So, it's all it says, this tightness result, is that there are convergent subsequences, but it doesn't tell us that all the convergent subsequences have the same limit. And we haven't been able to show that yet, but if it holds, then it will prove that the original sequence itself is convergent to that limit. But let me go on. So I was talking about the Markov state descriptor, and this is the Markovian state descriptor. So we use this descriptor to sort of prove our result. So here, basically, what happens is that we define these classes. So a class is the set of all jobs that uses the specific subset of D servers. So for example, this class of jobs uses the first two servers. This class of jobs uses the server 2 and server n and so on. So if you just describe the class occupancy at every time instant, so xni of t is the number of class I jobs at every time t, then this process is in fact Markovian. You can explicitly calculate the rate of xi in terms of the xi itself. Okay, so that's why it's a Markovian process. But it is still not, if you look at the empirical measure process, it's not a density dependent process, so we can't really apply the Kurt's type of theorem in this case. Okay, so one way of looking at it is as a bipartite graph, where the classes have edges with the servers, and the number of edges going out of a particular class is just D, and the number of edges coming into a server is n-1 choose d-1, because this is the number of classes a particular server is serving. So the Q length of a given server is just the summation of all the class occupancies of all the classes that the server is serving. So this is how we can express the Q length as a function of this Markovian state descriptor. Okay. All right, so I will not go into the rates. This is how you can compute the rates. One observation to make here is that from stability, it follows that pi n of 0, which is the fraction of, or the probability that the state will be in, the Q length will be 0 at stationarity, is just 1 minus lambda. It just follows from work conservation. And also our tightness results imply that, in fact, those class occupancies that I described earlier is going to 0. The stationary class occupancies are actually converging to 0 in probability. So this just follows from the tightness result that we had earlier. Okay, but it still does not give us the Q length. We are interested not in the class occupancy, but in the Q length, which is the sum of class occupancies over all the classes. Okay. So here, I guess I will not have too much time. So let me just quickly describe the mean field heuristics. So what happens, so we try to sort of take the physicist approach. It turns out it's quite hard to characterize exactly the limiting distribution pi. What we try to do is we try to make some reasonable assumptions and try to guess what pi should be. And then later on, we try to sort of justify those assumptions. So the approach we take is known as the cavity method in the mean field literature or the statistical physics literature. So we look at a given Q, and we assume that pi n in fact has a limit pi, and this the stationary distribution of this Q will be pi. This individual Q will be pi in the limiting system as n goes to infinity. And this will be interacting with an environment which is independent of the Q state itself. Okay, and that environment will also have the same distribution pi. Okay, so this is typically the assumption of the cavity method. And using this assumption, we will try to characterize the rate of transition from a given state of this server. So in this case, we can compute the rate of arrival quite easily. This is just d lambda. But the rate of departure from this, from the state where there are k jobs at a given server, obviously each job from this server will get a rate of 1 over k. But what is the rate that a given job gets from the environment process? This is where the complicacy lies. So under the mean field assumption, so assuming that the environment is sort of independent of the state of the tagged node, what we can sort of approximate this rate that the job gives, that the individual job gets from the environment as the sum over the d-1 other copies of this job. So obviously this job is present at d-1 other servers in the system, and the QJS is the Q length seen by the sth copy of that job in the environment. Okay, so this is how we define this variable QJS. It is the if you ask the copy what Q length do you see in the particular server you're in, then it will tell you a random answer, and that random answer is QJS. Okay, and we take the expected value because these are random, and we are talking about the instantaneous rate of departure, so we have to take the expectation to make the transitions Markovian, and we sum it over all the d-1 copies that are there in the system, in the environment. But how do we compute this QJS? So I would just like to say this, and perhaps I will not show the other results, other technical results. So we have to still compute the expected value of 1 over QJS to get the rate, right? Because the rate is just 1 over the sum of this d-1 rates. Now, to get the distribution of QJS, for we have to basically look at the environment. So we have, again, remember the definition of QJS is that we ask the sth copy of the job, what Q length do you see in the server, right? So now if you assume that the sth copy of this particular job is no different from any other copy that exists in the environment, then the probability that the copy finds itself in a queue with length I is just proportional to I times pi I, right? Because there are pi I servers or a fraction of the probability that you see a pi I server is pi I. A server with Q length pi I is pi I, the probability. And you can be any of these I copies that are present in this server. So the probability that you see a Q length I in the system is proportional to I times pi I, which is basically the size bias distribution. So to get the probability that the Q length is exact, the Q length seen by the copy is I, is basically we have to divide by this normalizing constant to get this probability. And then we can easily compute the expectation of this random variable QJS, 1 over QJS in fact. And this turns out to be just 1 minus pi 0 divided by E pi of Q. And E pi of Q is just the expectation under this measure pi that we have assumed to be the measure of the Q at cavity. Okay, so this is the rate that it gets. So expected value of 1 over Qjs is just this quantity. So we have to sum it over all d minus 1. So there is a d minus 1 factor coming in. And 1 over k comes from the tagged server itself. So the job gets a total rate of this much from the entire system. So now if we want to calculate the total rate of departure from the whole server, we have to multiply it by k, because there are k jobs and each of the jobs get this rate. So we get the total departure rate from the system to be this. Okay, and if we try to sort of formulate the detailed balance equation with these rates, then we come up with these equations, and we prove that in fact for lambda less than 1 and d greater than or equals to 2, there exists a unique solution to this set of equations, which is often called the fixed point equation. In this case, it's also the detailed balance equation. And we also show that for d greater than 2, in fact, the Q length under this distribution pi, which comes out as a solution of this detailed balance equation, satisfies this property that I mentioned earlier. So near lambda 1, when lambda is close to 1, the expected Q length is of the order of log of 1 by 1 minus lambda. Okay, so this sort of hints at the performance benefit of using d to be something greater than or equals to 2, some small d greater than or equal to 2. Okay, so this is obviously, we have assumed that there exists a mean field, and we have under that assumption of mean field, we have shown that there exists a unique solution, and this solution satisfies this performance criterion. Okay, so let me just close with some plots. So so this is a CDF comparison showing how accurate is this approximation with this the finite n. We see that the finite n CDF almost exactly overlaps with the mean field, with the CDF that we compute from the mean field. So this sort of supports the conjecture that I have written here. But we have made some significant progress also towards proving this conjecture. So in particular, we have sort of proved this monotonicity property, which says that if 2 copies of the system starts at 2 different states, then this dominance will be maintained throughout all the times, which is an essential property. And then using this property, we have shown that in fact, the convergence to the stationary distribution is uniform in n. So obviously we know by ergodicity that the Q-length distribution at time t is going to converge to the Q-length distribution, which is at stationarity, pi n. But this rate of convergence doesn't depend on the system size n. Okay, so this is a very important result, and we hope that using this important result, we can actually prove the conjecture, and we believe that we are pretty close to proving the conjecture, and even we have a valid guess for our the limiting process that we believe is the limit of the empirical measure process. And in this case, we are showing some plots to sort of support this guess that indeed as n goes to infinity. So here we are showing the cumulative complementary cumulative CDF obtained from the limiting process, and that obtained from the simulations. So you can see that we have increased n from 100 to 1000 and 5000, and we see that the noise basically disappears as n increases, and finally we sort of converge to this limiting deterministic process, which is the empirical measure process of a nonlinear Markov process. But we haven't been yet able to prove that in fact the Q-length process or the empirical Q-length process converges to this nonlinear Markov process Q, which has this distribution. Okay, so that remains as an open problem. And so just to summarize, we have shown that for large n and d fixed, we can get an exponential reduction in the mean Q length when lambda is close to 1 in comparison to d equals to 1 case. And we have also made significant progress towards rigorously justifying our mean field approximation. With that, I would like to end the talk. Sorry for overshooting by almost 10 minutes. If you have any questions.
Arpan, I request you to keep the slide on the stationary distribution that you had as a conjecture.
Oh, yeah, sure, of course.
So the green, the solid lines around which you have these the jitters are the solution to the multidimensional ODE. Is that correct? Starting at everything starts at 0.
Yeah, everything starts at 0. So we know that the finite system is in fact monotone. So in the sense that if we start at 0, we will converge monotonically to stationarity. Even for the finite system, we know that. But it's at the moment, we do not know even if there exists a unique solution to this equation, this set of ODEs. We haven't been able to show that this is Lipschitz or this is, this satisfies, I mean, the finite Pn process, which is the empirical measure process for finite n, whether it converges to this process P, we haven't been able to show. But one thing which I believe is not difficult to show is the global asymptotic stability property for this system. So you have to basically consider a Lyapunov function, which is basically the L1 norm between the P at any time, the empirical distribution at any time, and the pi that we conjecture to be our stationary distribution in the limit. And that L1 norm, basically, it's not difficult. Assuming that this has a solution, it is not difficult to show that, that L1 norm actually goes to 0 with T. So global asymptotic stability is not difficult if we know that there exists a solution to this system.
Is there a Markovian caricature for which this is the correct ODE limit?
So this is difficult to, the Markovian caricature, I would probably guess that the system, so it's very hard to construct, very hard to construct a nonlinear Markov process, right? So this Q process whose distribution satisfies this equation, it is a nonlinear Markov process. And the way you construct this nonlinear Markov process is essentially by looking at the limit of the Qn process, which is non-Markovian. So it's not clear as of this point whether there exists any Markovian caricature that we can approximate this process with. There might be, I'm not sure, but this is very difficult because because of this term here, because the rate essentially depends on the distribution at time t and also on the expectation. So this makes it difficult. In general, you will have just the just the distribution dependence, but for nonlinear Markov process. But here it's also depends on the expectation, and that kind of makes the process, to think about the process for finite end quite difficult. And even
just a comment there. I mean, if you know the distribution, you will know the mean also. So this is a derived quantity based on the distribution. So why does that cause a concern?
Well, this is just a technical difficulty, is because this expectation. So if you have this in the denominator, so it makes it difficult to sort of prove the Lipschitz property.
Okay, so it is from the point of view of maybe showing Lipschitz, etc. That is an issue. Okay, thank you.
Perhaps another slide I wanted to, sorry, was there any question?
No, Professor, you can go ahead.
Oh, sorry. I just wanted to show one graph that I couldn't show. So this is the performance comparison plot. So where I sort of show the average Q length for different values of D. And this is just in support of this theorem that we have shown. So here what we have shown is the for different D, we plot the average Q length, and we see that the highest drop we obtain near lambda equals to 1. So this is also sort of validates this theorem, because near lambda equals to 1, we know that it's going to be of the order of log of 1 by 1 minus lambda, whereas this is just lambda by 1 minus lambda. So we do have this exponential drop almost. But another interesting thing to note here is that we have taken D up to 10, and we are in the setting where n is 100. So we see that there is not much of improvement after D equals to 2. So once D is already 2, then the improvement is quite marginal. So the gain is mostly obtained by going from D equals to 1 to D equals to 2. So this is just insight that we have for the system. So that's all I wanted to say.
Thank you.
Okay.
Thank you, Professor, for the enlightening talk. As discussed before, we would like to remind the audience to subscribe to our Google Groups, which is the mailing list for information on future talks. You can also visit our website for more details, and the links have already been pasted in the chat box. The link to the recorded video will be posted on our webpage. Thank you, everyone, and have a great evening.